I'm going to try to write in a way that'll be visible. Do my best.
Should we close the blinds?
Would that help you? All right, giving it a few minutes to let everybody show up. I hope physics is going well for you, Liam. Do you still have that live stream up?
I can't.
Oh, I'm sorry. You're my test subject.
Where you got.
So that means I'll probably miss most of
Yeah, probably 20% of the lines that
facts.
yesterday.
I don't know what it was.
5 hours. I did all the MCQ and then Frankie unit 2. 5 hours.
It's like 4, 3, 2, or 1.
No, like 1 multiple choice, 1 FRQ,
Yeah, for
two
which
two multiple choice. Yeah, 1, 2. For unit 1 and 2.
Oh, okay.
I think here's something.
Caleb.
It's probably himself.
No, it's
No, it's not the Liam you think. It's
But I don't know, but it says Liam. Can I see my test without the curve? Because I didn't have any today.
I think you did. It's 9 o'clock yet. We're starting right at 9, so we can get you guys home. or to the beach.
I have another review after this anyway.
What are you gonna do?
I think an hour is going to be
Probably study
a long time. I don't think we'll need that long, but sometimes I tend to ramble. So, morning. So I'm going to do my best to ramble. Important stuff.
Really quickly.
Yeah.
Out of the 5 mechanics equations, which ones do we get on the equation sheet again?
You get the 3.
Okay. And which one is it?
We're going to go over that.
Okay.
Good question. I can't see the questions that are being asked in the live chat.
Oh, is that why I have them open?
I've never held a live event before, and I set it up incorrectly, so I have to use my phone. And then when I use the forward-facing camera, the stuff on the screen is a mirror image, so people...
No, you could just see the top. That's what I was talking
No, it was actually a mirror image. So I have to face the phone away from me. So I'll check every once in a while regarding these questions. But it's 9 o'clock, so let's dig in. Hopefully it goes well. If it doesn't go well, I already have this recorded.
Are you're just teaching us right now, kind of? Like it's just like
Don't worry about it.
like it's like we're not asking questions. We're just
You can ask questions. Of course, I would much rather this be a live question and answering situation than me just talking. I hate that, as you know. Hopefully. I don't have a microphone or anything. I hope you can hear me out there.
about.
Yeah? You sure? Okay. All right, so starting off with kinematics, remember that we have these scalar and vector quantities, and we have to know the difference between the two. Starting with the most basic, we have distance versus displacement. Displacement is your ending point to your starting point, the straight line that connects the two. Then we have distance, which is just the total amount of your path length that you travel. For vectors and any of the vector quantities we've talked about, we have to remember there's magnitude and direction. Whenever you see the word magnitude, you should remember that that means absolute value. So if it says magnitude of acceleration, that means we need to take the absolute value of our acceleration. Magnitude of gravitational potential energy, take the absolute value of that. For scalar direction, it does not matter. These notes come from the College Board's AP Physics 1 course and exam description. Going through these, I copied down this stuff a couple of years ago and have changed some things, added some things. Some things I'll have to rephrase in here, just be aware of that. But for the most part, this is going to work pretty well for us, I think. Just to get the basic ideas down as a refresher review. So some of our scalar quantities that we've talked about, we have kinetic energy, we have work, we have distance, we have speed, which we use letter V for. Time is scalar. These quantities don't have any direction. Meanwhile, the vectors we've talked about, velocity, angular velocity, we could also put angular displacement up here. Acceleration, angular acceleration, displacement, which I show with delta x. Delta is change, final minus initial.
What's the first one on the vector?
The first what?
V.
Velocity.
We have both.
We have speed for scalar and velocity for both. 10 miles per hour is a speed. 10 miles per hour in the positive direction is a velocity.
What is the difference between the two W's?
This is capital W for work, which is a scalar dot product of force and displacement. And this is not w, this is Greek letter lowercase omega for angular velocity. Onto our three kinematic equations. The big three kinematic equations, we have velocity as a function of time, Vf equals V naught plus AT. Then we have the no time equation, which is Vf squared equals V naught squared plus 2A delta x, so acceleration times our displacement. Then we have our displacement formula, which is x equals x naught plus V naught x times t plus 1/2 a t squared. On your equation sheet, all of these will be in terms of x, meaning that they only apply in the horizontal direction. But that doesn't mean you can't use it in the vertical direction. In fact, you should use it in the vertical direction. It's just then it would become y. And if you don't do that, free response, obviously that doesn't matter for this exam, but for a free response question, if you just use v naught x, but you were talking about things happening in the vertical direction, that's fine. Nobody's going to yell at you or mark you off for that. Those are the big three equations. There's also the fourth equation, which was our average velocity equals delta x over delta t. And from that, we can also get our average acceleration in our change in velocity over a change in time. To get our instantaneous velocity or our instantaneous acceleration, we have to decrease that change in time as time approaches 0. You can take the limit of that and you can figure out pretty roughly your instantaneous velocity or acceleration. As far as calculations go for AP Physics 1, you're not going to have to deal with that too much unless it's giving you a graph. If you have a graph where you have velocity as a function of time, and it looks something like this, and it wants to know your instantaneous velocity at 2 seconds, then you would go right here and you would read the graph to see what the instantaneous velocity is at that point. If we were looking for our average velocity between 1 and 3 seconds, then we would just draw a straight line and figure out the average of that. If this is a displacement versus time graph, and we wanted to know the average velocity, we could just do this straight line, figure out the slope of this straight line, and that would be our average velocity. I guess we could move right into position versus time graphs. Whenever you're given a graph, my big rule is for you to look at your action. What information are you given, and what are you expected to know from this graph? We know that the position as a function for calculus terms, instead of slope, derivative is used, and instead of area, we use integral. Those words are synonymous. So if I use one, if I say derivative, no, I'm talking about the slope. If I say integral, I'm talking about the area. Next, we have velocity versus time. And of course, we know the slope of velocity versus time is acceleration, and the area would give us our displacement. I wrote an X there before to say there was nothing important. That wasn't great. So we can figure out this area here. And if your area looks like something you have no idea what the formula is, I don't know what the formula is for that shape. So I'm going to cut it into pieces that I do know. I'll say there's a triangle. Here's a triangle. Here's a rectangle. Here's a rectangle. Here's a rectangle. Here's a triangle. Cut it into shapes that you do know the formulas for. Length times width. 1/2 length times width. Remember that whenever you pass the horizontal axis and there's still more information, that means we have stopped and changed directions. 0 velocity means we've stopped instantaneously, and changed directions.
If it hits 0, bounces back up, does that mean we change directions or
no? Nope, good question. We only change directions if we change positive or negative y's. So if we have a graph that looks like this, we haven't changed directions. That hit 0, don't let my drawing fool you. So we stop briefly, but then we continue moving in a positive direction. We know it's a positive direction because we're up in the first quadrant still, and when we take this area of both of these, that will give us a total positive displacement, which means we're still moving in the same direction, positive direction. The direction of your velocity is the direction of your motion. Slope of position versus time is velocity. Slope of velocity versus time, where the derivative of velocity versus time is acceleration. We can also look at our acceleration versus time graphs. And in acceleration versus time, we have this slope, which the slope of it is something called jerk, the rate that your acceleration changes. We don't need to know that, so don't worry about it. The area under the curve for this one is the important piece of information, and that's going to bring us back to our velocity. If you're having trouble remembering this, XVA in the vertical direction. As we go down, we take the derivative, which is the slope. And when we go up, we do the opposite, antiderivative, which is our integral, or the area. Yes?
There were some like graphs, I think on like one of the homeworks that had t squared instead of time. Like, what does that change? Like, versus is the slope still going to be?
Nope. So if this were velocity versus t squared, no, because that becomes v over t squared, and that is not what acceleration is equal to. If you're ever confused or in doubt of yourself, look at your units. Write the units out. We have meters per second over seconds squared. Right? So we'll have meters over seconds cubed.
What if it was like position versus time squared, then the slope of the acceleration?
Position versus time squared.
Yeah.
So with this, let's go back to our kinematic formulas, because this is a result of this displacement formula. If we have 0, if we start from 0, which is usually the case, then that term goes away. If we start with a velocity of 0, then this term goes away, and often what we're left with, the shortcut, would be 1/2 at squared. So if we have x versus t squared, excuse me, y equals mx plus b. So x is plotted on the y, t squared is plotted on the x. Your slope is half of your acceleration.
Okay.
Good question. Going the opposite direction, area under the curve for velocity versus time is displacement, and area under the curve, or the integral for acceleration versus time, will give you your velocity.
Is it like the average velocity in that time? Or is it
Yes. For vectors, and this will be true for any of our vector quantities, we have vector addition that could come into play. This is going to be magnitude 1, 2, 3, 4, 5, 6, 7. Magnitude 7, and this is going to be magnitude 1, 2, 3, 4. If I add these two vectors together, I can take vector A, draw it, and then take vector B, and pick it up, and move it. Oh, I thought I could. No, okay. Tip to tail. So I'm going to put the tail of vector B at the tip of vector A. And when I do that, what I'm left over with will be my resultant vector. I'll give you another one of those, just so it's a little bit easier to see. This, I'm going to say my magnitude is 5, and this will be a magnitude of 2. When I add them together, I'm going to redraw vector A, redraw vector B using the tip to tail method. My resultant is connecting the very beginning, my tail of vector A, to the tip of vector B. If there were a third vector here, I would just keep doing the same process. Make it go down. And we'll say it's magnitude of 1. So now I have 3 vectors, and I'm just adding them together, just combining them from the tail of vector A to the tip of vector C. Whatever that magnitude is, would be the...
Yeah, we don't have to solve for the magnitude of something like that, right?
Usually it's going to be a graphical thing.
Right angle.
Yeah. And always look for the right angle, if possible. Try to make a nice right triangle, because they're a lot easier to deal with. Can you see that there? You guys can read.
That's not
Go ahead.
Right.
No, wait. Vector subtraction is also a thing that may show up where you're kind of asked, we'll say vector A is 5 and vector B is 2, like that. If we're subtracting these two vectors, then that's the same thing as adding the opposite of vector B. So if I rewrite this problem, I get this. And my resultant would be 7 in that direction. When we subtract vectors, we add the anti-parallel.
So wouldn't you add the plus 2, not subtract -5? Would it be -7 too?
It's 5 minus 2
-5 plus 2.
is 5 plus opposite of 2. Whenever we have a vector quantity at some angle, vector at an angle, split it into horizontal and vertical components. We have this nice right angle that will show up, and it makes our life easier, especially if we're given some information like the angle from the horizontal that we're given. So now we can use trigonometry, make sure we're spelling SOHCAHTOA right. and we can solve for whatever it is we need. In the opposite direction, adding them in the same direction. Okay, there's the thing. See, I can't move to that. Good for me. We have a bullet fired versus a bullet dropped. Both H's are the same. It will take the same amount of time for them to reach the ground, because they were both being accelerated at the same rate. For any of our problems, we're using g equals 10 meters per second squared. This can be disguised in any way. If you're given a projectile question, it's more likely than not that it has to deal with this. You may be asked something differently, but a lot of times if we're looking at the horizontally launched projectile versus one falling straight down, the time will be the same. And that is an important piece of information that we can use to solve problems with. What I mean by that is whenever we have this parabolic motion, we get that parabolic motion from a velocity that's acting this way and an acceleration vector that's acting down. So that acceleration is changing the direction of your velocity. So if you have these two vectors interacting constantly, you're going to get a resultant vector downwards. And if you do that infinite number of times, you get this parabolic curve. We have three different types of projectiles. Type 1, horizontally launched. That's a key phrase that will be used to tell you it's this type of problem. So use whatever methods you've figured out or lessons you've learned to apply them here. So horizontally launched means that, well, we know the time will be the same. If we have horizontally launched versus vertically dropped, the time is the same for these two. So if we're given a height, we can find the time it takes for this thing to reach the bottom just by figuring out, okay, it starts from rest, so our initial velocity in the y is 0, our acceleration is 10 or negative 10, t is going to be whatever, and our final velocity is, we don't know. So we can use the displacement formula, x equals x naught plus v naught y, t plus 1/2 at squared to solve for t. But obviously we're not in the x, so if it makes you feel better, here's what I was talking about before. We can put all of these terms in terms of y. Our initial position is going to be less than or more than our starting position, depending on what you take to be positive and negative. We're taking down to be negative, then we're starting at a positive, and we're going to end up with a negative height here. The initial velocity in the y, if something is dropped, the initial velocity is 0. So what we get is y equals 1/2 gt squared. So we can do 5t squared equals h if we want. And then from here we can just solve for t and get the square root of h over 5. Should have given you a number there for h, but that's okay. Now I can take this piece of information that I use for my vertical drop and plug it into the horizontal formulas. So for horizontally launched, use free fall. Free fall is defined as being in a situation where gravity is the only force acting. So our tip here is going to use free fall to solve for time. Then use your horizontal equations. From here I can figure out, okay, maybe I want to find my range, which is my displacement along the x. How far away is it going to travel? I can use my displacement formula, x equals x naught, which is 0, v naught x times t plus 1/2 at squared. I know I have, if I don't have any air resistance, then I have no acceleration. And this term goes away, and what I'm left over with is x equals v naught x times t, which I solved from my vertically dropped situation. Plug it in from there and then solve for whatever. This v naught x, if it's horizontally launched, then my angle that I'm launched at is 0. So my initial velocity will equal my initial velocity in the x, because my initial velocity in the x equals my initial velocity times cosine of the launch angle. We can call that tip number 4. All of your initial velocity is in the horizontal direction. Questions on horizontally launched projectiles? Okay. Honestly, if you see a horizontally launched projectile, you can go through all of this stuff here and deal with time, but we know better. We know it's got a speed, which is kinetic energy, and we know there's a height involved, which is gravitational potential energy. So we can just use conservation of energy here also, depending on what we're asked for. If we're asked for this range, no, we can't. We're stuck. But we can figure out the final speed just before it hits the ground using conservation of energy. Second type of projectile. Launched and caught at same height. These are the beautiful parabolas, the full thing. Caught, launched at the same height. And we can use reasonable assumptions here to get to the same height. If you have a quarterback and a receiver throwing a football, we can assume they're the same height, and the launch height is the same as the catch height. Make the problem easy on yourself. For this, our first tip is to keep x and y values separate. Does anybody have the live stream up by any chance? Yeah, are there any questions? Oh, good, everybody's quiet. Is anybody even in there? Okay. Hi, everybody. So the x and y values have to be separate. What that means is this ball or cannonball, dog or whatever is launched at some angle. Probably won't be a dog. It's launched at some angle. Whenever we have a vector at an angle, we can resolve it into its x and y components using trigonometry. So in this case, our hypotenuse is our initial velocity. Then we have our initial velocity in the x and our initial velocity in the y. Those two separate pieces are working together to create that velocity at an angle. V naught y is on the opposite side, so it's going to be our hypotenuse times sine of our launch angle. For the x direction, it's going to be hypotenuse times cosine of our launch The next thing is to remember this is parabolic motion. And we love parabolas because of symmetry. That means whatever happens on the left half is exactly a mirror image of whatever happens on the right half. So if this thing is launched at 30 meters per second, it's going to come crashing down at 30 meters per second. Negative 30 meters per second, mirror image. With this symmetry, we can cut this in half. And we know that our final velocity in the y will equal 0 at the top of this trajectory. Does that mean we don't have any velocity in the x direction? No, we still have velocity in the x direction, still carrying it to the left or to the right, whatever you see. It just means for a brief instant, whenever we throw something up, it's slowing, 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 slowing. Stop, and then its speed turns, changes direction, and starts moving faster and faster and faster in the opposite direction. We can use that bit of information to find time, which is usually what we're going to do. And it doesn't matter which side of the parabola we're using. We can use the front side with our launch velocity being given to us, or we can use the back side with our launch velocity being given to us and figure out the time that it takes for it to come down. Doesn't matter, whatever's more comfortable for you. Also, because it's stopped at the top, that does not mean that gravity stops working. There's still an acceleration down at 10 meters per second squared. These problems take some time, unless there's an obvious quick thing, like ball is launched at 30 meters per second, is in the air for 8 seconds, find the speed just before it hits the ground, something similar like that, then we know we can just spit out a fact. Or at the top of at its maximum height, What is the acceleration? We know it's just going to be 10 meters per second squared down. Those are quick facts. If it's not a quick fact, if it's something where you got to dig in and really go through, then this question is what I would call bread. If you haven't heard the analogy before, I think of the AP exam as a buffet. And if you've been to a buffet, they're not putting the good stuff up front. You're not getting the meat right there. You're not getting the desserts first thing. Instead, they're putting the bread first in hopes that you'll pick that because it's going to fill you up and it's cheap to make. So, of course, wherever you're eating at wants you to eat the bread because you're going to fill up and you're not going to have room for all of the good stuff. So if you're eating the bread, you're wasting your money